Hey guys, and welcome back to another video on the channel. Today's topic is a bit of a new one, so we're going to be going over eigenvalues and eigenvectors today. So this is pretty much like a topic in linear algebra and matrix algebra. So, pretty much you basically see these things pretty much with matrices. So, let's consider we had a matrix, let's say A, okay? So I'm going to use capital letters to indicate matrices and lower letters or lower variables such as like X with an arrow to indicate vectors, okay? So suppose we have some matrix A, okay? And you multiply it by, so let's say this is a square matrix. So we'll define it as, just say, all right, this is A1, 1, dot, 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 goes over to AN, 1, and this is like let's say AN1 and this goes to ANN. Okay, so this is a square matrix. So this is an n by n matrix. So there's n number of rows and n number of columns. So if we multiply this matrix, we can multiply it with pretty much any matrix such that it is equivalent to the rows pretty much. So you can multiply this matrix by an n by 1 matrix, or an n by 2, yada yada, as long as you have an n by something, as long as the number of rows matches the number of columns of this matrix. So in other words, if you have an n times n and you want to multiply it by an n times like m, and this m is some other number, as long as these two numbers are the same here, you can pretty much do it. And what the beauty is, the product will be basically the n. It'll be basically n multiplied by m as your number of rows. So your product, what you'll get when you multiply this matrix by this matrix, you'll get a n multiplied by m, okay? Now, what we consider with this special case is, let's say we had this square matrix, and you multiply it by a vector, okay? So a vector with the same number of rows, okay? So let's say we had a n by 1 vector, okay? So let's say this vector looks something like this, okay? So it's got, let's just use this, keep using the square brackets for this. It's equivalent to here. And say we had, let's say this is x1 dot 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 all the way to xn, pretty much. Okay, so this, pretty much this vector has the same number of rows as it does columns here, okay? So if, let's say we consider this matrix and this vector here, if we multiply these, pretty much these quantities together, if this vector here is an eigenvector, pretty much what you'll get as a product is going to be pretty much a multiple of that particular vector. So this is basically what eigenvalues and eigenvectors mean in linear algebra. If you take a matrix and you multiply it by a specific vector and you get a multiple of that vector, so this symbol here basically means a scalar. So lambda basically means any real number. So what this notation means, this symbol here means belongs, and this big R here basically means all the real numbers, okay? So you could have, it could be a multiple, lambda could be pi, lambda could be -5/3. As long as it's a multiple of that vector, then x with the arrow on top, this vector here is an eigenvector then. So why is this important? Well, you can basically apply this problem to solve all sorts of problems in engineering and physics. But in this video, we're just going to show you how we actually work out what these eigenvectors and eigenvalues are. So this here is pretty much your eigenvalue. So it's basically the multiple that you're getting out of. So what we have to consider is basically a very simple case. We cannot consider the this vector here as the 0 vector, okay? So it cannot be the 0 vector. What that basically means is basically we can use that to basically try and make an expression here, okay? So what we're going to do is basically we're going to try and solve this whole thing in terms of a thing that we can pretty much solve. So what we're going to do is basically move this term over to the other side. So we're left with matrix A multiplied by the vector minus this part here. Now, since we're dealing with vectors, this 0 here on this side isn't just the number 0, it's the 0 vector. So it's like this vector here with the same number of rows as these matrices and this vector has, okay? So as you can see, we can take out a common factor of this vector, so we can take out this vector here, and we're left with pretty much this. Now, what we can do, basically here, we can do a little algebra trick. We can basically say that this bit here, so lambda multiplied by this vector, is equivalent to lambda multiplied by the identity matrix multiplied by the vector. Because the identity matrix is pretty much the number one in matrix world. So the identity matrix basically just has ones down the diagonal. So this is a 3 by 3, for example, where it just has ones down the diagonal. Okay, so this is a 3 by 3 example, but you can have up to an n by n. Okay, it's a square matrix, so we can pretty much apply this here because it physically, these are equivalent. It's not going to change anything algebraically. It's just a little trick that we're going to use when we're simplifying and making a formula to determine these eigenvalues. So we have this matrix A minus lambda multiplied by the identity matrix is equal to the 0 vector. Okay. Now, this is where a little trick comes in pretty much. Okay. So, what are we saying here? We basically, alright, for this scenario to work, we are looking for a vector such that it is not this 0 vector here. Basically, what that means is basically this product here is going to be a matrix. But this matrix cannot be invertible. I'll tell you why. Because let's say it was invertible, okay? And when we're not looking for this vector, we are looking for vectors such that this vector here is not equal to the 0 vector. So if this matrix was invertible, we'd have the vector multiplied by the inverse of whatever this matrix is, multiplied by this, multiplied by the inverse on this side, multiplied by the 0 vector, okay? Now, an inverse multiplied by itself is just going to cancel. So we're left with basically x is equivalent to, so an inverse, no matter what matrix you have, if you multiply by the 0 vector, you're going to get the 0 vector. But we don't want this. We are looking for a vector such that it's not the 0 vector. So what we are saying here is basically this matrix is not invertible. So that gives us a little trick. So recall, if you have a matrix, let's say you have a 2 by 2 matrix. So let's say you had a matrix B. B is, let's say, is a matrix where it's like, all right, B1, B2, B3, B4. The inverse of this matrix here, so B inverse, is going to be 1 over the determinant of B. And then you switch these around here. So you have B4, then you change the sign here. B2, negative B3, and B1, okay? So that's what happens when you have an inverse matrix. But notice this particular property. No matter if you have an inverse matrix, you have this 1 over the determinant here. So, if this matrix here does not have an inverse, the determinant here must be 0. Because let's say this B's matrix didn't exist, it didn't have an inverse, then its determinant would be 0. So what we can say is basically, all right, to work out our eigenvalues, we can say the determinant of this matrix here, so we write it as delt of A minus lambda I, basically has to be equal to 0. And this is pretty much the formula we use to determine eigenvalues, okay? And once you determine an eigenvalue, all you need to do is plug it back in up here, and then you can work out your eigenvectors, okay? Alright, so now that we've established that, let's put a lot of this to the side. So, I'm just going to make this smaller and move it over a bit, okay? And we'll move this up here, alright? Alright, let's do an example. So, let's say you had the matrix. Alright, let's just stick with A. So, A is the matrix -2, 1, 1, -2, okay? And we want to determine the eigenvalues of this. So we want to determine basically what these values here are, such that if you multiply A by a vector, you get a scalar of that vector. So we'd find the eigenvalues first, and then we can determine our eigenvectors, such they aren't the 0 vector, okay? So all we got to do is basically plug this into our little formula up here. So we write, all right, the determinant, or you could rewrite it. So another way writing determinant of a matrix. So if you're looking for the determinant of A, you pretty much can write this matrix just as a square matrix with these long lines here. So if you write it like this basically means, alright, the determinant of that matrix, okay? Alright, so, but before we do that, let's just simplify this formula we have in here. So we're just going to write it, alright, delt brackets our matrix A, so we'll have -2, 1, 1, -2. Then you're going to subtract lambda, multiply by our identity matrix, which is 1s down the diagonal, but it's a 2 by 2, because we're dealing with a 2 by 2 here, so we'll have 1, 0, 0, 1. Delta of that is equal to 0. Now we can distribute this because this is just a scalar, so we can distribute this into the matrix. So we're left with basically delt of our matrix A, -2, 1, 1, -2, plus we can leave we can just put the negatives inside with the lambda, or you can leave on the outside. So I'm just going to bring this whole thing into the matrix. So we're going to have pretty much matrix A plus negative lambda, 0, 0, negative lambda. Now these stay zeros because negative lambda times 0 is still going to be 0. So we leave it like that. And then we can add these matrices together on the inside because they're the same size. So what are we left with? We're left with basically the determinant of this matrix here. So we'll have -2 minus lambda, 1, and then you have 1. So, alright, 1 minus 0, and then you have 1 minus 0, oh no, well, plus 0, and then you have -2 minus lambda, okay? These aren't going to change at all, because if you add nothing to something, then you're still going to have that something, so we just still have the 1s there. So this is what we're left with, okay? Now, what we do now is basically we find the determinant of this. So recall, if you have some matrix like this, so let's say we had matrix, let's use a different letter again, we're using A a lot. Let's say we had matrix Q, and you had A, B, C, D, and you want to find the determinant of Q. That's equivalent to basically multiplying these two numbers together, subtract the product of these two numbers together, so C, B, okay? So we'll do the exact same thing here. So we're going to multiply these two numbers together. So what we're left with is basically, alright, -2 minus lambda multiplied by -2 minus lambda. Now you notice these two things are the same, so we can rewrite it as basically a square. So we can rewrite it like this. And then we basically have the multiple of these two minus. So -1 times 1, which is just 1. So we're left with this. Now this is pretty much a polynomial now. Now we basically got to solve this. So this is going to give us a quadratic. So if I just get rid of this square again and just rewrite it like we had it before, basically going to do the FOIL method now. So first outer inner last. So we're going to multiply -2 by 2. Then we're going to multiply -2 by negative lambda. Then negative lambda by -2. And then negative lambda by negative lambda. So first off, -2 times -2 is +4. Then we have -2 times negative lambda, so you're going to have +2 lambda. Then you're going to have negative lambda times -2, which is +2 lambda. Then you're going to have negative lambda multiplied by negative lambda, which is going to be positive lambda squared minus 1, okay? -1 plus 4 is going to be 3, so we're left with lambda squared. 2 lambda plus 2 lambda is 4 lambda. So we're pretty much left with this, right? Now, you can solve this quadratic however you want. You can use the quadratic formula, or you can just pretty much break it up into its like products. I think that's the word. No, it's factors. Yeah, that's the right way to use it. So, from straight off, I know that this is equivalent to lambda plus 1 and lambda plus 3. Yeah. Reason this is because if we multiply this out, we're going to get what we have up here. Because, alright, 1 times 3, that's going to give us 3. Then 1 plus 3 is going to give us 4. So this is pretty much it. And if you multiply this out, you'll get, alright, you're going to get lambda squared plus 3 lambda plus 1 lambda plus 3, which is equivalent to what we have there. So this is basically it factorized, okay? Now, what does this tell us? So this basically tells us one of two things. When you have it something like this, whether it's a quadratic or anything, okay? So If you multiply these two quantities together, you're going to get 0. That means there's two cases. That means this thing has to be 0 or this thing has to be 0. We can't tell which one is going to be 0, but we have to account for both. So we basically say, all right, when does this bit here equal 0? When lambda equals -1. So our first solution is lambda is equal -1. And then we have to account for this bit here. This bit could be 0 as well. So what does lambda have to be for this bit to be 0? Lambda has to be -3. So these are our eigenvalues, okay? Now, what do we do with those now? So we've gotten that. Now, I'm just going to write it up here now. So we have lambda is equal to -1 and lambda is equal to -3. So we've determined our eigenvalues. Now we're going to determine our eigenvector. So I'm just going to move all this working to the side real quick. All right, so let's take, there we go. Let's do it from the bottom actually. There's not enough room on my drawing tablet. I'll just have to select it one at a time. Alright, move that up there, and we'll move this out of the way. And we'll just move that down there, okay? If you want to copy any notes or anything, you're going to probably have to skip back into the video. Alright, let's go now, up here. So what's the point of finding these eigenvalues? Well, what we're trying to find is basically a vector such that if you multiply it by this matrix, you're going to get a scalar of that vector. So we're basically looking for matrix A multiplied by some vector is going to give us basically a multiple of that vector. Now, we've basically determined what these multiples are. So what we can actually do to work out our eigenvector is pretty much rearrange this equation. Now, I wrote it down just before. So the way we're going to do this is basically we're going to do same thing that we did before. We're going to move this bit here over to the other side. So we're going to have matrix multiplied by this minus, and then we're going to put the identity matrix in there because we're dealing with matrices, not just numbers. So we'll have lambda I matrix V is going to be equal to the 0 vector. Okay. You can take out the factor of a vector. So we'll have A minus lambda I and our vector here. So all I've taken out was this vector because it's common in both of these terms here, is equal to our 0 vector, okay? Now we're going to define our vector here, this is our eigenvector, as just in these terms of coordinates. So we'll have the x coordinate as just like x1, x2, and x3, okay? So, and we have our matrix here, so we're going to rewrite this whole thing as pretty much, all right, we're going to have -2, 1, 1, -2, this matrix, plus negative lambda, 0, 0, negative lambda, 0, multiplied by this matrix here, which is x1, x2, x3, is equal to our 0 vector, which is just 0, 0, 0, okay? Combining these matrices in here, we can simplify that a lot more into just a normal 2 by 2 than instead of 2 by 2. So we'll have -2 minus lambda, and then you have 1, and then you have 1 here. Then you have -2 minus lambda. Okay, so this is our matrix here, and this is multiplied by a vector. Oh, this is a 2 by 2, not so we don't have a third component. Sorry, I was thinking of a 3 by 3 matrix. Okay, cool. There we go. Righto. Now this is much easier to solve. Now recall, we can basically determine two equations pretty much because we know what lambda is. Lambda has to be -1 or lambda has to be -3. So we basically can choose. So let's just do lambda equals -1. So we'll substitute that into there. So we're going to be left with pretty much the matrix. All right, -2 minus -1, which is just going to be -1. That's going to stay the same. That's going to stay the same. -2 minus -1, which is going to be -1 again. Okay, so we have this matrix multiplied by this vector here is equal to the 0 vector. Okay, now we can break this up into two simultaneous equations. Okay, so the rows times the columns. So this entire row here multiplied by this column here. So what we're left with is pretty much, all right, -x1 plus x2 is equal to 0, and then you have this bottom row here times by this column here, and we get two equations. So we have 1x1 minus x2, okay, is equal to 0. Now, all we need to do is solve one of these equations. So, what does this tell us? Well, basically, if we rearrange the first equation, these equations are pretty much identical, because if you were to add equation 1 and equation 2 together, like, alright, you add this equation here, that bit's going to be 0, and that bit's going to be 0. So that equals 0, 0. So you can use either one of these equations. It doesn't really matter to work out your eigenvector. Now this is the tricky part, okay? So let's take equation 1, and let's move the 1 onto the other side, okay? So we have x2 is equal to x1, okay? What does this mean? It means, basically, whatever our vector x is, such as x1, x2, in order for it to be an eigenvector, these two numbers need to be the same, okay? Now, we know that it has to be pretty much, the eigenvectors have to be -1 or -3. So we basically make this pretty much assumption. So in order for it to be an eigenvector, let's just choose any number pretty much, okay? So let's say we chose the number, let's choose the vector 5, 5, okay? So if we were, I'm just going to double check on my calculator I've done this right. So if we had the matrix 2 by 2, so we have negative, what was that matrix? -2, 1, 1, negative 2, multiply that by, alright. So basically, it doesn't matter what numbers we put here now, because we've been given a general expression for our eigenvector. You can put whatever number you want here, as long as these two are the same. So let's say we went with, alright, the vector 5, 5, okay? If you multiply this vector here by this matrix here, -2, 1, 1, -2, if you multiply that, that's going to give you the vector -5, 5. Now, if you take out a common factor of -1, that's your eigenvalue. So what you have actually been given is basically an infinite amount of eigenvectors, such that, alright, this vector here has to be in this form, where you have like, alright, k, and k has to be the same number, and it can be any real number, okay? So your first eigenvector, with the eigenvalue -1, takes on this form. For example, let's say we chose a different set of numbers. So let's say we chose 6. Actually, no, let's choose an even better one. Let's say we chose like 16, okay? If you were to put that into your calculator, 16, as long as the x and y components of this vector are the same, you're going to get -16, -16. Now, you take out a common factor -1, which is your eigenvalue, you get a multiple of that vector, which is an eigenvector. So this is your first eigenvector pretty much, okay? Now, so that's your first general form. What about your second one? When lambda is equal to, let's say, 3, because there's two eigenvalues, remember? So now let's replace that here. So what are we left with? Let's rewrite this. So we're going to have -2 minus 3, 1, 1, -2 minus 3. Multiply this by your vector. Alright, x1, x2 is equal to the 0 vector, okay? This will give us another set of simultaneous equations. So this bit here is going to simplify to, what's that? +3 plus -2, so it's going to be pretty much 1, 1, 1, 1, okay? Multiplied by x1, x2, okay? Now you notice, we're going to get two of the exact same equations together. Because if we multiply this matrix by this vector, we're going to go, alright, row times the columns. That's going to give you the equation x1 plus x2 is equal to 0. And it's going to give you the exact same thing again when you multiply the second row by the vector. So let's just deal with this equation here. So what does this mean? Alright, if you switch onto the other side, you have x1 is equal to -x2, okay? So what does this say about our second eigenvector? Pretty much, your second eigenvector is basically going to be, you can have any number, let's say q, but its y coordinate needs to be the negative value. So they have to be the same values, but this bit here has to be the opposite sign. That's why it's got the negative. So for example, let's see, let's put our matrix down. So let's say we had -2, 1, and let's say we had, 1, -2, and we multiply that by, let's say, let's think. I'll just think of an example real quick. Alright, let's say we did 6 and -6, okay? If you multiply that together, you're going to get -18 and 18. Now, if you take out a common factor of -3, you're going to get your original vector. And this is your eigenvalue. So this is your second eigenvector. So Q can be any number. It doesn't matter, as long as it looks like this, okay? And this will give you when your eigenvalue, so lambda is equal to -3, okay? Alright, I hope that was a good video. If you have any questions, please leave some in the comments. This is my first actual matrix video I've done on the channel. If you did enjoy it, please like and subscribe. I've recorded this video for a student that I'm tutoring at the moment. If you do have any more questions and you want more matrix videos done on the channel, please like and subscribe.